Welcome to qnawire.
Okay, so problem number 13 asks that a certain atom requires 3.0 electron volts of energy to excite an electron from the ground level to the first excited level in a box and find the width L of the box. So if we start with equation 40.31 from the text, which gives the energy of the of each level of a particle in a box, E sub n is equal to n squared h squared divided by 8 ml squared. And now we know that, okay, so we're exciting it from the ground level, which is E1, which is equal to 1 squared, which is just 1, so h squared over 8 ml squared, and up to state, which is E2. So E2 is equal to 2 squared, so I'll just 2 squared h squared divided by 8 ml squared, which is just equal to 4 h squared over 8 ml squared. All right, so now this 3.0 electron volts is the amount of energy it takes to excite the transition from the ground state to the first excited level. So that's the difference in energy between between these two levels is equal to E2 minus E1, which is equal to 4h squared over 8 ml squared minus h squared over 8 ml squared, which is equal to 3h squared over 8 ml squared. So this is also equal to the energy, 3.0 electron volts, that it takes to excite the electron from the ground state to the first excited state. All right, so now what we want to do is solve for L. So we will say, so we have 3.0 electron volts is equal to 3h squared over 8 ml squared. All right, so now we multiply L squared over here, bring delta E over, we get L squared is equal to 3h squared over 8 m times 3.0 electron volts. All right, 3.0 electron volts. Okay, so now, or L is equal to the square root of 3h squared over 8m times 3.0 electron volts. Okay, so now I'm going to write that again here. Over 8m times 3.0 electron volts. Okay, so now H is Planck's constant, which is 6.62. Sorry. 6 times 10 to the minus 34 joule seconds. M is the mass of an electron, so we'll call that M sub E, which is 9.11 times 10 to the minus 31 kilograms. And now we want, since H is in terms of joules and mass in terms of kilograms, we want this energy in terms of joules as well. So we use the conversion. 1 electron volt is equal to 1.6 times 10 to the minus 19 joules. All right, so now we plug all these numbers in. We get L is equal to the square root, I will leave that open-ended for right now, 3 times 6.626 times 10 to the minus 34 joule seconds squared divided by 8 times 9.11 times 10 to the minus 31 kilograms times 3.0 electron volts. Keep this going. Times 1.6 times 10 to the minus 19. That's supposed to be a 10 joules per electron volt. All right, let's close this. You do all this math here. And you get that the size of the box, L, is equal to 6.1 times 10 to the minus 10 meters, which is equal to 0.61 nanometers, or 6.1 angstroms. Now, 3 eV is, so just a kind of a note about these energy scales, 3 electron volts is kind of the typical energy level for an atom. And like the optical band gap of titanium oxide, which is a semiconductor that's used quite readily, is 3.0 electron volts, and 6.1 angstroms is on the order of bond lengths. So these are pretty, modeling this as a particle in the box is a pretty reasonable approach.